Hello everybody, I hope you are doing great. In the last few days I've been writing firmware for microcontrollers and more specifically peripheral drivers for some peripheral modules that have to interface and exchange data with the MCU. And I had some peripheral modules on hand and thought why not to make a video of explaining the whole process of reading a peripheral IC datasheet and extracting the necessary information in order to write a simple driver for an STM32 microcontroller that initializes the peripheral and transmits and receives data. Before we start, I want to let you guys know that if you like these kinds of videos, to like the video and subscribe to the channel, because we are going to have more of these videos in the future, and this also motivates me to do more videos and help the channel grow. So in this video we're going to write a firmware driver for the BU9873 IC, which is a real-time clock IC that interfaces with I2C. We are going to go through the datasheet and explain a simple driver I've written in the STM32 Cube IDE. I'm also going to leave a link at the description for the GitHub repository where I share the driver code and the header files, and the peripheral datasheet with some important notes I did. So let's get started. So when we write a driver for a peripheral we don't know about, it's a good idea, before we focus on the stuff we care, to browse carefully to the whole datasheet, and once we do that, then to focus on the necessary stuff. The necessary stuff that you have to look for is what communication interfaces the peripheral uses, which can be more than one, because the peripheral might use one to initialize and one to communicate and interface data with the microcontroller. Next thing that you have to go through is the pin description section that gives some info about the pin configuration of the peripheral, and also to take a quick look at the electrical characteristics, because this might change the way the peripheral operates. Once you do all this, then you have to take a quick look at the interface information, because it might share some details for the peripheral interface that differs in operation comparing it with other applications in other peripheral ICs. So finally, the next thing that you have to look for is a basic configuration section, and more specifically the register maps, because these supply all the register addresses where you are going to write configuration settings and use them to exchange peripheral data. So if we go through the datasheet, as you see here, the BU9873 is a CMOS real-time clock. It has interrupt generation and uses I2C interface to interface with the microcontroller. Some of the features, as you see here, that it has time settings, it has hour, minute, second, and selectable 12-hour, 24-hour mode. It has calendar, periodic interrupt, and also alarm interrupts. You can also use the IC to have a clock output. And if we check some of the characteristics here, the important characteristics, you use voltages from 1.45 to 5.5 volts. And as I said at the beginning, as you see here, the access frequency is 100 kHz max when we've got a VDD of 1.8 to 2.5, and from 2.5 to 5.5 volts we've got 400 kHz max clock frequency, which is actually what I said in the beginning, that you have to check for the characteristics before you write drivers, because these characteristics will change the way the interface works. If we scroll down here now, you see some typical application circuits. We're not gonna go through this section because we've got a readily available module that has all the components on the PCB, but this is important if you want to make your own PCB that uses this IC, and you have to put all the components on your own. We've got the pin configuration, we've got all the outputs, the inputs, we've got the interrupt pin, we've got the pins for the crystal oscillator, the external crystal, the SDA and the SCL pins that are the pins for the I2C interface. So we don't have anything important here, and if we scroll down, we've got a basic diagram of how the IC works. And this is actually very simple. We're not going to go through this, but this block diagram helps a lot if you have a very complicated IC that has a lot of working sections, and you have to see all the sections and try to figure out what configuration settings you have to write in order for all the processing and power sections to work correctly. So we've got some maximum ratings here for the voltages. These you have to check those if you don't use a module and you use the IC on your design. You have to take a look at those. We've got some more DC characteristics here, and if we scroll down, we see some characteristics for the I2C interface, and these are the same as at the start that I said. We've got for different VDDs, we've got different max clock frequency of the I2C interface. So if we scroll down here, we see some performance curves. These are important when you want to select a component that has the performance that you might look for, and you basically check those in peripherals that have ADCs and DACs, and you care more about the noise performance and the frequency response and the frequency performance of the IC. In this section we see some basic explanations of the functions that the IC has. There's a section for the communication interface, address maps for internal registers where you're going to write data and configuration data, a clock and calendar function where it's going to describe some of the functions of the clock and calendar functions. There's a section for the alarm, and there's also sections for tests, second adjustments and oscillation halts, and this kind of stuff that we're not gonna go through, and we're gonna go through only the necessary sections that we're going to use them to write the driver. Here we have the communication interface section. As you see here, the I2C data communications starts with a condition bit. It has the data length is 8 bits, and there's always a signal after each byte. There are two wires, as we said in the beginning. There is a clock wire and a data wire, and this peripheral works in slave mode, and actually the microcontroller, that means that the microcontroller, which is the master, drives the clock for the data and the send and receives of the peripheral. So if we see here, we've got the start condition. There are bits, highs and lows. This actually explains the whole process of how the I2C bus works. Some things that we have to take note of is the address of the IC. In order to communicate with the IC, you have to pass the address of the IC to the function that is used to communicate with the IC. So in this case, the slave address is 0110010, which is the address that we use to communicate with the IC. And if we take a look at the next paragraph, it says that the input the internal in the next byte after the address byte, we input the internal address pointer, which is 4 bits, and the transmission format, which is 4 bits, to the IC. For write operation, only one transmission format is available, and the third byte transmits data that will be written to the address specified by the internal pointer, the internal address pointer. So that basically says that when we want to have a write command, there is a start bit. There is, after that start bit, there is a slave address byte, which actually indicates the address of the peripheral. And after this byte, we've got one byte that the most significant bits are used as an internal address pointer, which is going to tell the peripheral where to write the next bytes of data that are going to go through the data line. And there's also a transmission format. So as you're gonna check in the code, the internal address pointer, because it is 4 bits, you actually have to take that internal pointer from the register maps and shift it 4 bits to the left in order to create that whole 1 byte address, which is consisted of the internal address pointer and the transmission format. Also, at the end of this paragraph, it states that internal address pointer settings will also be automatically incremented for 4 byte and after. And that actually means that if you start from example from a register with address 0, so you write the slave address, you write the pointer address with the transmission format, which is actually 0, and the third byte is this one. So if after that third byte you write a 4th byte, then the internal address pointer is gonna increment to the next address, and it's going to write that data in the next address. So in this case, if we have the start address 0, after in the 4th byte, the 4th byte is going to be written in the address, register address 1. And this can happen for more bytes than 4, right? Here we've got the read command that actually explains the same process as in the write command. There is an internal address pointer, a stop condition, and a start condition. And actually, when you start, when the master sends the slave address to communicate with the peripheral and the internal address, there is an acknowledgement bit that actually says to the peripheral IC to send the data back to the master. If we scroll down, there are some more configuration for the I2C communication. You can actually fast read from an internal address. There is if we change the transmission format, we can then a register address without every time passing the address. There are some notes here that during data transmission that you have to look for. We are at the address mapping of the internal registers. So here we've got all the addresses, all the available addresses that you have to write and read data from. And these addresses, as I said in the above section, you have to shift this address 4 bits to the left, so you create the 1 byte address that has the internal address, and the less significant bits, the 4 less significant bits, are the bits for the transmission format. So as you see here, we've got the address of the second counter, which is actually 7 bits. We've got the minute counter and a register for the hour counter. We've got the day of the week, the date counters for the year, month and day. We've got a time trimming register. We're not going to write in this because you actually write in this register if you have clock offsets, and you have to compensate that error and make the necessary calculations in the IC in order to output the correct time. We've got alarm registers for the day of the week register, the hour register, and the minute register. And we actually have 2 alarms, alarm A and alarm B, which are used, and they are working independently. And the last 2 registers are used to write configuration data that actually initialize some of the settings and the functions of the clock. So we're gonna check those bits here. As you see here, each bit represents a setting, and when you write a bit 1 or bit 0, that actually indicates a different setting. We're gonna go through the controller register settings in more detail once we continue to the data. So if we check now at the clock and calendar function, it says here that the clock and calendar functions are working in BCD mode, and actually if you want to write the time and date data at the IC, you have to convert the binary time into BCD time, because the IC is gonna count in BCD mode, which is actually different from the binary. So if we check the clock counter here, it gives a basic function of how the clock counter works. There's a minute counter, a second counter, as we said. And now we go through the configuration registers, and here it says that we've got a selection for 12 and 24-hour mode. And actually if we write at that bit, we write 0, it's gonna initialize to 12-hour time display system. But if we write 1 at this bit in the configuration address, it's gonna be in a 24-hour time display. So here there is a display table for all the digits in different hour system display. And the next thing that we're going to look for is the alarm interrupt function. And actually this function uses an interrupt pin that it says here that when the day, the week and the hour of minute match with the preset time that we set on the alarm, this interrupt pin goes from high to low, and that actually indicates an alarm. It says here that there are two systems of alarms and they work independently. So if we take a look at the usage of the alarm interrupt, it says here that users can set time and generate an alarm. So these are the addresses specified for the alarm A, and you have to again here write the BCD values for the minute and the hour registers, and then write an alarm day, write data day of the week in the day of the week register. And as you see here, this register is actually different from the other the day of the week register that uses the counter, because in this case you might use the alarm for more than 1 day. So you need to have a memory function that actually you can input more than 1 days of the alarm. So this actually works as a truth table, and you actually write 1 to each bit indicating a day that you want to trigger the alarm. So for example, if 0 is Sunday and 6 is Saturday, as it goes on the date, on the week of the day registers, if you write 1 here and 1 here, then you're going to have an alarm in Sunday and an alarm in Saturday, which actually works as a truth table that compares the bit with the day register counter. Here we've got some examples of alarm settings that work in 12-hour system and in 24-hour system. And if we scroll down, we see here that the alarm interruption is enabled only when alarm enable and B alarm enable, A alarm enable and B alarm enable are set to 1. So if you see here, alarm A and alarm B are default set to 0, and you have to write 1 in the bit that corresponds to alarm A enable and alarm B enable, which if we scroll up, that means that you have to go to write to controller register 1, which is this address, and go and write, if you want to enable alarm A, you have to write 1 in the 8th digit bit. So if we continue here, This section explains how the interrupt alarm pin actually works, and it states here that the alarm interrupt output is from the interrupt B pin, and it's outputting low, as I said in the beginning. When the interrupt is triggered, the interrupt pin is writing low at the pin. It states here that if we read the value of A flag, A alarm flag and B alarm flag, you can check the state of the alarm. So if we go to configuration register 2 and read the bits of the A alarm flag and the B alarm flag, these bits are going to indicate the state of the alarm. So if this flag is 0, then there is an unmatched alarm, which is default, and if we read 1, then we've got an alarm and the interrupt is actually low. And that actually we can actually see the timings here, that when we've got when the flag is 1, we've got the interrupt pin low, and that actually indicates an alarm. The last thing that we have to check here is that it says here that the flag bit turns to 1 and interrupt B is low when match time and sensed is sensed for each alarm. That's actually the function of the alarm. The important thing that we have to check here is that it says that the flags may be set only to 1, and setting this bit to 0 sets the interrupt to off, status high. So if we've got an alarm and we want to reset the alarm, not delete the alarm date and time, weekday and time values, but we want to reset it, we have to go to the flag register, the flag bit, the register that corresponds to the bit flag, and write 0 to that if we want to reset the alarm. If we continue here, there are some information about how the interrupt works when we've got 2 alarms triggered at the same time, but in our example we're going to just initialize the clock and the day and trigger only alarm A in the drivers, so there is not a lot of important info after this last page here. That was the whole process of reading and understanding how the peripheral works. And actually, if you want to understand in detail how the peripheral works, it actually takes more time to read the whole datasheet and try to understand how in depth the IC works. And actually, if you think about that, when the peripheral is not simple and it's more complicated, there is actually a bigger datasheet that has more register maps, more configuration data that you have to write to configuration registers, and this actually gets a lot more complicated. But in general, that's the whole process of reading a datasheet and understanding how the IC works. Next up, we're going to CubeID and show you how all this information from the datasheet correspond to actual code. So if we go to the driver source files, as you see here, I've created a source file and a header file, and this is actually good practice because it's better than writing it right here at the main .c source file, because you might want to use this in a different microcontroller, and if you've got different source files and header files, you can actually go to main, go to the header file and just include the header, which is going to input all of the functions written in the header file. If we actually want to create a header file, we just go to File, New, and we go to Header File. And actually you select the folder here, which is core ins, and you write the header file with .c at the end to create the header file. If you want to create the source file, you just do the same thing and create the source file. And when you want to connect the header file with the source file, you have to include the header here at the source file, because the compiler is going to connect those two files and create the interface that is going to be used to communicate with the code at the source file. So as you see here, I have included the HAL.h header because I'm going to use I2C handle the function, and more specifically I'm going to use the memwrite and memread functions that actually implement these data reads and writes to the memory addresses and the configuration addresses. If we check here, these two functions get a pointer of the I2C handle def. It's getting the device address, the memory address of the register that we want to read data to, the address size, a pointer that corresponds to the data that we want to read or write at the registers, the configuration registers, and the size of the data, because we might want not to just write 1 byte, but we want to write 4 bytes. So we're gonna write here 4 bytes if we want to send on or receive 4 bytes. And there is also a timeout parameter that you are going to just input how much time you want the microcontroller to count before it actually stop trying to communicate with the peripheral. Next thing here that we look is the device address. As we said at the beginning, the device address is 0100110, which is actually in hex it is 32. As we see here, it's 0x32, and you actually have to shift the bits to the left one time to indicate that it is a slave address. One other good practice is to write at the header files or the definition of the configuration register addresses and use those to input them to the functions that read and write data, because if you actually write the addresses directly to the functions, you might do a mistake and actually you will not write the right value, and this will create more confusion, and you will try to search for the mistakes. But here you've got all the important addresses at one place, and if you've got a mistake, it's going to be here, and you don't have to change the addresses on each function call. So as you see here, we've got the addresses for the seconds counter, we've got an address for the alarm values, and some addresses for the date values, and actually got those values from the register map here. As you see here, there is here at the left, you are going to see the values written in hex. We also have the controller registers here. These registers are E and F, same as here. And then it's a good practice to do some definitions of the data that you have to write in controller registers. And in this case, in our application, we want to enable alarm A, which is actually in the controller register, it is the bit 8, the 8th bit. So we write 80 at control register 1. At register 2, we want to enable clock, and enable clock is actually 0. And we also want time type of 24 hours. So we need to write bit to write 1 at the 5th bit. So this is actually 2 0 because we've got 0 at those and 1 at the second 4 bits. And then we need to use the alarm flag if we want to reset the alarm. If the alarm triggers, we have to write 0 at the flag to reset the interrupt. If you see here, I did some definitions of RTC errors. These are actually optional. I'm just using them in order to check what error I have and if I have any errors. I did the definition here for the returns. That's a simple type def that these functions return. We've got a struct for the time, and if you see here, we've got seconds, minutes and hours in 8-bit unsigned, and we've got a date struct for the date. Next up, this is a struct that is going to be initialized with all the necessary parameters that are going to be used from the peripheral functions. And if you see here, I've got a GPIO, port and a pin number that I'm going to use these for the interrupt pin. There is a struct for a struct pointer for the I2C because we're going to use this struct and pass it to the I2C functions in order to read and write data. We've got some initial controller register values that we have to store because we might want to use a second alarm and we just want to know what's the last controller register value, so we don't just write 0 here and reset both of the alarms and not only the one that we want. And lastly, RTC holds a time struct and a date struct. So the necessary functions that we're going to use, we've got an RTC init that is going to initialize the controller registers and the RTC struct. We've got a set time and a set date function that is going to set the time and the date at the IC. We've got a get time and a get date that actually reads data from the register counters that count the date and the time and store them in the date and the time struct. We're gonna use a function that sets the alarm, that actually writes the alarm enable bit, and the reset alarm that actually clears the flag, and also a disable alarm A that actually disables the alarm and writes 0 to the enable bit of alarm A. Lastly, we're gonna have a simple get alarm pin that actually reads the GPIO of the interrupt pin. And as I said in the datasheet, you actually have to write BCD data to the time and date counters because the IC counts to BCD. So you have to take the binary value of day, month, year, and etc. and convert it to BCD and then write it to the registers, to the register counters. And if you want to get time and date, you have to convert BCD back to binary in order to know what you read. So if we continue to the source file, the source file actually has here a simple explanation of how the code works. And as you see here, we've got the RTC init function that initializes the struct parameters with the I2C type def, the interrupt port and the interrupt pin. And as you see here at the memWrite function, we pass the dev address, which is shifted to 1 bit left. We pass the controller register address, which is actually 4 bits left shifted because the datasheet says that you have to shift the address, the register address 4 bits. We've got 1 byte of register address, and we have a data that the address of data that actually passes the address of the data variable into the pointer of the memWrite function, and that actually gives a simple check if the memWrite returns HAL OK, and if that doesn't return HAL OK, then we're gonna have RTC error and it's gonna return RTC error. Then we do the same for the second controller register that actually writes the time type and the clock enable, which time type is the 24-hour counter type, and it does the same thing and returns RTC OK at the end if both of the functions return correctly. Here at the set time, we actually initialize an array with 3 bytes. We pass second, minute and time to the time struct, and then we have to pass those values into the array, but actually convert it from binary to BCD, as I said before, because the IC counts to BCD. Then we pass again the address of the IC, the second counter address, because this address is actually the first one, the first one, and actually as the datasheet states, after the 4th byte, you can actually the internal pointer address actually increments by 1, so you can write 3 bytes here, and each one of the data has to be in the correct order in order to write seconds at the second register, minutes at the minute register, and hours at the hour register. And that returns again RTC error if it doesn't return correctly. At set date, we do the same thing again. We convert binary to BCD. We write at the weekday counter address and the date data and 4 bytes. And actually I write first day of the week counter because it's actually the first one, and the next registers are incremented, or addresses are incremented automatically. So on get time, when we want to read time, we have to execute the read function, and we do the same thing, but this time we pass the pointer of the array to the memRead function and read 3 bytes, because we can do the same thing as we do with the write function, and we have to take those data and pass it to BCD to binary function to convert BCD back to binary and read the values correctly. We do the same with get date, and then at set alarm we again have the array here with the data. On the weekdays, as we said in the alarm, the weekdays are actually like a truth table, so you just indicate which day to trigger the alarm, and it's not just one number. And then because you want to enable the alarm, you have to take the initial value of register 1 and do a bitwise OR with the alarm enable, and that is going to return the correct register value that is going to be written and enable the alarm. So we do a memWrite for the register value and a memWrite for the registers for the minute, hour and weekday counter for the alarm. Then we have a reset alarm that actually resets the flag, and that as the datasheet states, you have to go to the bit that indicates the alarm flag and write 0 in order to reset it. So we do that, and at the end there is a disable alarm function that actually takes the value that the initial value together with the enable alarm if it's enabled, and applies a bitwise AND with the complement bit of the alarm enabled. So for example, if we've got 0, 1 for the alarm and we apply a bitwise OR, this is going to enable and this is going to create the whole value and enable the alarm. If we take the complement, it's going and apply an AND bitwise AND. This is going to put the opposite value of what value would enable the alarm, and then we write that final value using memwrite. As you see here, we've got a basic get alarm pin that actually reads the GPIO, and if it is in 0 as the interrupt pin states, it's going to return 1, and it's going to return 0 if the interrupt pin is high. Actually return 1 here because I want to put this in an if statement so I don't have to do comparisons and stuff. And lastly here I've got the two necessary conversions from BCD to binary, and if you actually search for those, they are widely explained at the internet, and because this actually video takes long, you can actually check it on the internet and see how the conversion works. We're now going to test the code. As you see here, I've initialized all the necessary handle defs. These handle defs are initialized automatically. So here in pin assignment, I've enabled the I2C interface at those pins, the interrupt input at this pin that actually writes that to that pin if the interrupt is low. And actually, as I said in the datasheet, at the power rating function, you might need to check those settings because you might have a clock speed that is faster than the appropriate, and you have to do the fine adjustment to those settings. But in this case, I put it 50 kilohertz clock speed, which is fine. I call RTC init to initialize the clock. So I pass the address of the RTC struct that I initialized at the start. I pass the address of the I2C handle def and the port pins and GPIO structs. I set the time, so I pass the time numbers, the seconds, minutes and hour values. I set the date to second weekday from 0, so this is going to be Sunday, Monday, Tuesday, the value Tuesday, and I initialized some basic date here. So I also have set alarm A to trigger at 0 minutes at 0 hours, so that is going to trigger on midnight. And I also have put it here the bits that indicates which day for the alarm to trigger, and in this case, if we start, this is Sunday, we've got Monday, Tuesday and Wednesday bits to be 1, so this alarm is gonna trigger Monday, Tuesday and Wednesday. So at the while loop here, I get the time and I get the date, and if I have alarm pin to be 1, then I delay 5 seconds and then I reset the alarm. So if you want to test the code, we press the debug pin, the debug button. As you see, this is going to compile the code and flash the microcontroller. And if we actually do it in steps, we initialize the alarm, we set the time, we continue. If we wait 2-3 seconds, we execute get time, and as you see here, we've got 46, which is actually 6 seconds later than the set time. If we get date, it's gonna get the correct date. As you see here, I set the alarm to 00, and if you're gonna check the module, the interrupt pin actually triggered, and if we continue here, it's gonna get into the if statement, it's gonna delay 5 seconds, and then reset the alarm. And the light of the module actually turns off, which is actually indicating that the alarm was reset. As you see here, I've got the setup. I've got the module and the STM32 flashed with the same code as in the video, and I've resetted the STM32, and as you're gonna see in a few seconds, the red LED turned on, waited for 5 seconds, and then it's gonna reset again as the code states. So we have successfully implemented a firmware driver for the RTC module. So this was the whole video of explaining how to process a datasheet and write a basic firmware driver for a microcontroller. This video actually took more time than expected. It was I finished it in 40 minutes, but I think I got into more detail, tried as good as I could to explain the whole process. I hope you liked the video, and don't forget to leave a comment down below if you liked the video and you want more videos like this in the future with different peripheral components. You can also write me in the comments if there is something I want to cover more in detail in the next videos, and also if you want to implement some code for an interrupt that happens in the MCU once the alarm is triggered, so we execute different code if the alarm is set. And also give me a like and subscribe to the channel if you want to get notified for more videos like this. So thanks for watching, thanks for hanging out, and I'm gonna see you in the next video. Goodbye.